Sometimes the assumption for our chi-square test is not that everything is occurring randomly, but rather that our data will match a pre-established pattern. This is called a goodness of fit test with known proportions, or what I'm going to call a no difference test, that what we observe will be no different than what we expected from our comparison population. So how do we find our expected frequency in this setup? What we're looking for is whether there is or is not a difference from a comparison population or a set of comparison proportions. So let's say that we know the public favors a proposal 60-40. We would expect that the values that we would achieve in any particular sample would be around 60% to 40%. Now, when we're comparing to known values, to get an expected frequency, we're going to multiply n by the known percentages. We'll have to do this for each category in our sample, and we'll calculate the expected values multiple times. Let me use an example to help illustrate what I mean by no difference from a comparison. Let's say that we know in Missouri there's this ballot issue where 60% of people favor, 35% oppose, and 5% are undecided. Those are going to be our comparison values. When we do the survey in Arkansas, we find that 58% favor, 36% oppose, and 6% are undecided. Is that a good fit? Yes, it is. It is not much different from the comparison. Small differences, slight differences, but it's a good fit. When we take this same survey from Iowa, we find that 42% favor, 54% oppose, and 4% are undecided. Is that a good fit? It is not. Because the proportions in Iowa are different. They're going the opposite direction. So this is not a good fit. It is different from our comparison values. Let's do an example. We know that blood type varies among different populations of people. So in the United States, types O, A, B, and AB make up 45%, 40%, 10%, and 5% of the population respectively. So suppose that blood types are collected for a sample of 140 people from a foreign country. The raw numbers that we get from that foreign country are 42, 64, 20, and 14. What we want to know is whether there is a significant difference between this distribution and what we would expect in the United States. All right, let's go back to our table and let's do the math. The first thing that we should ask ourselves is, what is the appropriate statistic? And it is the one-way chi-square test. Our null and alternative hypothesis. This time our null is going to be that the distribution will be the same in blood type as in the United States. So same distribution of blood type as the United States. Our alternative hypothesis, not the same distribution of blood type as the United States. And we could be more specific and we could list the name of the other country and so forth. Now, our level of significance. How many categories are there? 4 blood types, degrees of freedom equals 3. Our alpha level should be set at 0.05. With 3 degrees of freedom, we go to our chi-square critical value table and we find that the expected value, or rather the critical value, will be 7.81. Now we're going to calculate the statistics. In our table, we start with column 1, writing down the observed values. These are the raw scores, the raw counts from the comparison country. Now we need to get our expected values. Remember, there were 140 people who were sampled. Now, if the other country matches what we expect for the United States, we should get proportions of 45%, 40%, 10%, and 5%. But we must multiply those percentages by 140 to get each expected value. So we'll do this one at a time. We multiply 140 times 45%. That's a value of 63. Then we multiply 140 times 40%. We get a 56. 140 times 10%. That's easy, it's 14. And 140 times 5%, that would be 7. So now we have written in our expected values. Notice that those expected values have to be calculated every time. So for each of our observed values, we will calculate an expected value. Now, the rest of the procedure works exactly the same as we've already learned. To fill in column 3, take the observed value, subtract the expected value, and write down the answer. 42 minus 63 is a negative 21. 64 minus 56 is 8. 20 minus 14 is 6. 14 minus 7 is 7. To fill in column 4, we will square the value in column 3. Negative 21 squared is a positive 441. 8 squared, 64. 6 squared, 36. 7 squared, 49. And now we take the O minus E squared, the value from column 4, and divide it by the value in column 2. Remembering that the value in column 2 is different on each line. So we do not divide by the same number each time. This time we start with 441 divided by 63. And that gives us a chi-square for that row of 7. Then it's 64 divided by 56, 1.14. 36 divided by 14, 2.57. And 49 divided by 7 is 7. The last step is to add up these chi-square values for each line to get the total chi-square, 17.71. Now let's go back to our 5 steps. We have calculated a statistic of 17.71. The critical value we were looking for, 7.81. So are we over the fence with 17.71? In the critical region? Yes. Yes, we are. So the distribution of blood types is not the same as in the United States. Chi-square with 3 degrees of freedom is 17.71. P less than 0.05. Now there's one more important thing that I want to tell you about, and this is true no matter what type of chi-square you're running, and that is that we want our expected frequencies to be above a certain level. Now, bottom line, this means that we need to have a large enough sample size for the chi-square to work. But when we have small numbers of expected frequencies, that can produce an error in our chi-square. So small number of expected frequencies in a cell can produce an error. The cell is really referring to one of the lines. Now, 80% of the cells should have at least a frequency over 5. So 5 becomes our important number here with chi-square. Most of the cells need to be over 5. If not, the chance of a type 1 error, in other words, a statistically significant chi-square when it really is not, that assumption or that risk goes dramatically up.